Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Filter 1 under the paper Measurements and Instrumentation. So students, let us see what we are going to learn in this module. In this module, the various types of electrical filters are discussed. The difference between active and passive filters is studied, and the advantages of active filters are highlighted. The various types of active filters are studied in detail. Types of practical active filters are discussed. The expressions for gain in a first-order low-pass and second-order low-pass filter are obtained, and frequency response is discussed. The expressions for gain in a first-order high-pass and second-order high-pass filter are obtained, and frequency response is discussed. Filters are the electrical circuits that allow a specific band of frequencies to pass through it without any attenuation. That is, output is approximately equal to the input, and it attenuates other frequencies which are lying outside the band. That is, output is nearly zero for those frequencies. Thus, all the filters have at least one pass band and one attenuation band, which can also be known as stop band. The frequencies that separate the pass and attenuation bands are called cutoff frequencies. Filters are used widely in the circuits which require separation of signals according to the frequencies. Some of the common applications include audio signal shaping and sound enhancement, channel separation and signal enhancement in communication circuits, smoothing of digitally generated analog signals, etc. Let us discuss the classification of filters. Electrical filters may be classified in various categories as analog or digital, active or passive, and audio or radio frequency. Analog filters are the filters which are used to process analog signals using analog techniques, while the digital filters are used to process analog signals using digital techniques. Filters are classified as active and passive depending on the type of elements used in the construction. That is, a passive filter is designed using passive components such as resistors, capacitors, inductors, while an active filter is built using active components such as transistors or op-amps in addition to passive components. The operating frequency of the filter depends largely on the type of element used in the filter. For example, RC filters are used for audio or low frequency signals, whereas LC or crystal filters are used for radio frequencies. Depending on the range of operation of the filter, it may be classified as audio frequency or radio frequency filter. Active versus passive filters. The simplest approach to build a filter is using passive components such as resistors, capacitors, inductors, etc. Passive filters operate well for radio frequencies, but for audio frequencies, inductors are not preferred as they are large, costly, and dissipate more power. Also, at low frequencies, in order to increase the inductance, more turns of wire are required, which add up in the series resistance, thereby degrading the performance of inductor. Despite the simplicity in design of filters using passive components, active filters are more preferred for practical applications due to the following advantages. First is gain and frequency adjustment flexibility. Since transistors or op-amps are capable of providing the gain in the circuit, therefore, the input signal is transferred to the output without any attenuation. This is in contrast to a passive filter where some drop in voltage takes place across the passive components. Also, it is easier to adjust the frequency range in active filters. Second advantage of active filters is that it prevents loading. A passive filter has low input impedance which loads the source. Also, it has high output impedance which provides poor load driving capability. Load impedance is not isolated from the passive filter components. Therefore, any variation in load alters the filter response characteristics. On the other hand, op-amp offers high input impedance and low output impedance, which prevents the loading of the source or load. Also, the load is isolated from the frequency determining network and thus it will not affect the characteristics of the filter. The third advantage of active filters is its low cost. Active filters are more economical than passive filters because of the easy availability of cost-effective op-amps in comparison to inductors which are costly. Active filters are widely used in the field of communication and signal processing. In fact, they are an essential component in almost all electronic systems such as radio, television, telephone, radar, space satellites, biomedical equipment, etc., and are thus discussed in this module. Let us now study the classification of active filters. As discussed before, active filters use op-amp as active element and resistor and capacitor as passive element. Depending on the frequency range allowed to pass through the filter, active filters are classified as number 1 low pass filter, 2 high pass filter, 3 band pass filter, 4th band reject filter, and 5th all pass filter. Low pass filter. A low pass filter allows all frequencies below the high cutoff frequency FH to pass through it and attenuates all others. Thus, it has a constant gain from 0 to FH Hz, which is shown in the figure. Bandwidth is given by FH. At FH, the gain reduces by 3 dB, and at frequencies F greater than FH, the gain decreases with increase in input frequency. The frequencies lying between 0 and FH are called passband frequencies, and those lying beyond FH are attenuated and hence called stop band frequencies. The filter response for an ideal low-pass filter is also shown in figure by a dashed line for comparison. It may be seen that an ideal filter has zero loss in its passband, that is, in the frequency range lying between 0 to FH, whereas it has infinite loss in its stop band, that is, for frequencies F greater than FH. It is difficult to realize the ideal filter response in practical applications because linear networks cannot produce discontinuities. However, it is possible to obtain a filter response that approximates the ideal one by using high-speed op-amps, special design techniques, and precision components, etc. Let us discuss the types of practical filters. Some of the most widely used practical filters that approximate the ideal response includes Butterworth, Chebyshev, and Coyer filters. Butterworth filter has a distinct characteristic of having a flat passband and a flat stop band, due to which it is also called as maximally flat or flat filter. Chebyshev filter has a ripple passband and a flat stop band. It has a sharper cutoff frequency than Butterworth filter, but Because of the presence of ripples in the passband, it has the drawback of appearance of various gain maxima and minima below the cutoff frequency. Kaya filter, also known as elliptic filter, has ripple passband and a ripple stopband. Generally, Kaya filter gives the best stopband response among the all three filters. Also, it has the sharpest roll-off in the transition region. The frequency response of various types of practical active filters is shown in the figure. Out of the various types of filter, Butterworth filters function as excellent general purpose filters and are the most widely used. In addition, Butterworth filters offer the advantage of simplicity in design and are thus discussed in the module. A high-pass filter, as shown in figure, allows higher frequencies to pass through it without attenuation. The gain increases with increase in frequency till the lower cutoff frequency FL and has a constant gain thereafter. Thus, a high-pass filter has a stop band from 0 to FL Hz and it has a pass band for frequencies F greater than FL. A band-pass filter allows a particular band of frequencies lying between a lower cutoff frequency FL and a higher cutoff frequency FH to pass through it. Here, FH is greater than FL. As shown in the figure, the gain increases with increase in input frequency till FL becomes constant for frequencies lying between FL and FH and decreases thereafter with further increase in frequency. Thus, it has a passband for frequency F lying between FL to FH and two stop bands for frequencies F greater than FH and F lying between 0 to FL. Bandwidth of a bandpass filter is given by FH minus FL. A band reject filter works exactly opposite to that of a bandpass filter. It rejects or does not allow a specific range of frequencies lying between the cutoff frequencies FL and FH, where FH is greater than FL. On the other hand, it allows all other frequencies as shown in the figure. Thus, it has two passbands for F lying between 0 to FL and F greater than FH, and a stop band for frequencies F lying between FL to FH. Center of the stop band in band reject filter, or we can say pass band in band pass filter, is called as center frequency SC. A band reject filter is also called as band elimination or band stop filter. An all-pass filter, as the name suggests, allows all frequencies to pass through it without attenuation, as evident from the equal amplitudes of input and output voltages in figure. There is a phase shift between the input and output signals and as a function of frequency. The highest frequency up to which the input and output voltages remain equal in magnitude is dependent on the unity gain bandwidth of the op-amp. However, at this frequency, the phase shift between input and output is maximum. Let us now discuss about the order of a filter. The frequency response of all types of filters in its stop band either steadily decreases or increases or both depending on the type of filter. The diagrams for the frequency response are already discussed. The order of a filter is determined by the rate of change in going from pass band to stop band or vice versa. For example, in a low pass filter, for F greater than FH, the filter is called as a first order low pass filter if gain rules off at a rate of 20 dB per decade. Let us discuss the first order low pass Butterworth filter in detail. The circuit diagram for a first order low pass Butterworth filter is shown in the figure. The circuit uses a RC network for filtering. Op-amp is used in the non-inverting configuration so that it does not load the RC network. Gain of the filter is determined by the resistors R1 and RF. According to the voltage divider rule, the voltage at the non-inverting terminal V1 can be written as V1 is equal to minus J into XC divided by minus JXC plus R into Vn. Since minus of JXC is equal to 1 divided by J into 2 pi Fc, therefore substituting in the above equation, we get V1 to be equal to Vn divided by 1 plus J into 2 pi FRC. Now, we know that output voltage in a non-inverting amplifier V0 is related to the input voltage V1 by the equation V0 is equal to 1 plus RF by R1 into V1. Therefore, substituting for V1, we get V0 is equal to 1 plus RF by R1 into Vn divided by 1 plus J into 2 pi F RC. So, the ratio of output to input voltage V0 divided by Vn is equal to AF divided by 1 plus J into F divided by FH, where V0 by Vn is the gain of the filter as a function of frequency. F is the frequency of input signal. AF is equal to 1 plus RF by R1 is equal to gain of the filter in its pass band. FH is equal to 1 by 2 pi RC and is equal to high cutoff frequency of the filter. The gain magnitude and phase angle equations of the low pass filter can be obtained by using the equation for the ratio of output to input voltage as modulus of V0 by Vn is equal to AF divided by square root of 1 plus square of F divided by FH. The phase phi is equal to minus of tan inverse F divided by FH. The above equation describes the operation of the low pass filter as follows. First, for very low frequency, that is F much less than FH, modulus of V0 by Vn is approximately equal to AF. Second, at high cutoff frequency, that is F is equal to FH, modulus of V0 by Vn becomes equal to AF divided by square root of 2, which equals 0.707 into AF. Third, for frequency greater than high cutoff frequency, that is F much greater than FH, modulus of V0 by Vn turns out to be less than AF, which is the flat pass band gain. Thus, the frequency response of the first order low pass Butterworth filter is obtained as shown in the figure. The designed filter has a constant gain equal to that of a non-inverting amplifier in the frequency range varied from 0 to FH Hz. At high cutoff frequency, that is F is equal to FH, the gain reduces to 0.707 of its constant value, and after FH, it decreases with increase in frequency at a constant rate. When the frequency is increased 10 times, that is, by a decade, voltage gain is reduced to 1/10 value. That is, it reduces by 20 decibel. Hence, the voltage gain rolls off at a rate of 20 dB per decade for frequencies f greater than fh. The frequency f is equal to fh is called the cutoff frequency, as at this frequency the gain of the filter is reduced by 3 decibels, and it is the minimum change in power that can be resolved by human ear. Cutoff frequency is also called as corner frequency, break frequency, or -3 dB frequency. For frequencies f greater than fh, the gain of second order low pass filter rolls off at the rate of 40 decibel per decade. Therefore, the denominator, which is quadratic in S, must have real and equal roots. For real and equal roots, the condition is RC prime plus R prime C prime plus RC plus AF RC divided by RR prime CC prime equals 4 divided by RR prime into CC prime. The root of the equation S will be equal to -1 by 2 into, within the brackets, RC prime plus R prime C prime plus RC plus AF RC divided by RR prime CC prime. This can be simplified to be equal to -1 by 2 into 2 divided by square root of RR prime CC prime, using the above condition for real and equal roots. Now J times omega h will be equal to -1 by RR prime into CC prime. This gives the value of omega h to be equal to 1 divided by square root of RR prime into CC prime. FH will be equal to 1 by 2 pi into square root of RR prime into CC prime. The voltage gain magnitude equation is given by modulus of V0 by Vn equals AF divided by square root of 1 plus F divided by FH raised to power 4, where AF is equals 1 plus RF by R1 and is the passband gain of the filter. F is the frequency of the input signal. FH is equal to 1 by 2 pi into square root of RR prime into CC prime. FH is the high cutoff frequency of the filter. The frequency response of the second order filter is shown in the figure. It is similar to the first order high pass filter. However, here the gain rolls off at a rate of 40 dB per decade. Let us next discuss about the second order low pass filter. Second order filters are important in electronics because they can be used to design higher order filters having very high roll-off rates. By cascading first and second order filters, filters of nth order for both even and odd values of n can be easily constructed. The easiest procedure of making a second order filter is to cascade two first order active filters, but this is not preferred as the circuit uses two op-amps. Alternately, a first order low pass filter can be converted into a second order low pass filter where the gain rolls off at a rate of 40 dB per decade by including an additional RC network as shown in the figure. As for the first order low pass filter, the gain of the second order low pass filter is decided by the resistors R1 and RF. However, the cutoff frequency FH is a function of resistances R and R prime and capacitors C and C prime. In order to derive an expression for the cutoff frequency of the filter, the circuit is transformed into S domain where S is equal to j omega as shown in the figure. Applying Kirchhoff's current law at node VA, we have I1 is equal to I2 plus I3. Or equivalently, I can write Vn minus Va divided by R is equal to Va minus V naught divided by 1 by Sc plus Va minus V1 divided by 1 by Sc prime. Using the voltage divider rule, V1 can be expressed in terms of Va as V1 is equal to 1 divided by Sc prime into Va divided by R prime plus 1 divided by Sc prime. This can be simplified to obtain V1 to be equal to Va divided by 1 plus S into C prime R prime, or Va is equal to 1 plus Sc prime R prime into V1. Now, substituting the value of Va in the above equation describing the Kirchhoff's current law, we get Vn minus within the brackets 1 plus Sc prime R prime into V1 divided by R is equal to within the brackets 1 plus Sc prime R prime brackets close into V1 minus V naught divided by 1 by Sc plus within the brackets 1 plus Sc prime R prime brackets close into V1 minus V1 divided by 1 by Sc prime. Solving for V1, we get V1 to be equal to R prime into Vn plus R prime into Rc into Sv naught divided by within the brackets R prime C prime S plus 1 brackets close into within the brackets R plus R prime RCS brackets close minus R. Since V naught is equal to AF times V1, where AF is equal to 1 plus RF by R1, therefore V naught is equal to AF times within the brackets R prime Vn plus R prime Rc into Sv naught divided by within the brackets R prime C prime S plus 1 brackets close into within the brackets R plus R prime RCS brackets close minus R. Solving for V naught by Vn from the above equation, we obtain V naught by Vn is equal to AF divided by S square plus within the brackets RC prime plus R prime C prime plus RC plus AF RC divided by R prime C prime brackets close into S plus 1 divided by R prime C prime. Let us now begin with the first order high-pass Butterworth filter. The design of high-pass filter is complementary to that of a low-pass filter and can be formed using a non-inverting op-amp by simply interchanging the position of frequency determining resistor and capacitor in low-pass Butterworth filter. The circuit diagram of a high-pass filter is shown in the figure. According to the voltage divider rule, the voltage at the non-inverting terminal V1 can be written as V1 is equal to R divided by minus jXc plus R into Vn. Since minus jXc is equal to 1 divided by J into 2 pi Fc, therefore, substituting in the above equation, we get V1 is equal to V times J into 2 pi F RC divided by 1 plus J into 2 pi F RC. Substituting for V1 in the expression for output voltage in a non-inverting amplifier, that is equation 2, we get V0 to be equal to 1 plus RF by R1 into Vn into 2 pi F RC divided by 1 plus J 2 pi F RC. This can be simplified to obtain V naught to be equal to 1 plus Rf by R1 into J times 2 pi f Rc divided by 1 plus J into 2 pi f Rc into Vn. Or equivalently, the ratio V naught by Vn is equal to AF into, within the brackets, J into F by FL divided by 1 plus J into F by FL, brackets close, where V naught by Vn is the gain of the filter as a function of frequency. F is the frequency of input signal. AF is equal to 1 plus Rf by R1 is equal to gain of the filter in its passband. FL is equal to 1 by 2 pi Rc is equal to low cutoff frequency of the filter. The gain, magnitude and phase angle equations of the high pass filter can be obtained by using equation 10, which is the ratio of V naught by Vn, as modulus V naught by Vn is equal to AF into F by FL divided by square root of 1 plus F by FL whole square. Phi is equal to tan inverse FL divided by F. The above equation describes the operation of the low pass filter as follows. First, for very high frequencies, that is F much greater than FL, the ratio F by FL is much greater than 1. Therefore, modulus V naught by Vn can be simply approximated to be equal to AF. Second, at low cutoff frequency, that is F is equal to FL, modulus V naught by Vn is equal to AF divided by square root of 2, which equals 0.707 into AF. Third, for frequency lower than the low cutoff frequency, that is F much less than FL, modulus of V naught by Vn is less than AF. The frequency response of the high pass Butterworth filter as described is shown in the figure. High pass Butterworth filter allows all frequencies greater than FL to pass through it with a gain equal to that of a non-inverting amplifier, that is AF. The frequency FL is called the low cutoff frequency and corresponds to the frequency at which gain reduces to 1 by square root of its constant value. At frequencies lower than FL, gain of the high pass filter decreases with a constant rate. We next take up the second order high pass filter. Similar to the first order high pass filter, a second order high pass filter can be formed from second order low pass filter by interchanging the frequency determining resistors and capacitors, or it can be viewed as formed from a first order high pass filter by including an additional RC arm. The circuit diagram of a second order high pass filter is shown in the figure, and the corresponding frequency response is also described. The cutoff frequency FL can be obtained in a similar way as done for a second order low pass filter by transforming the circuit into S domain. The voltage gain magnitude equation of the second order high pass filter is given as modulus of V naught by Vn equals AF divided by square root of 1 plus FL by F raised to power 4, where AF is equal to 1 plus RF by R1 equals passband gain of the filter. F is the frequency of the input signal and FL is equal to 1 by 2 pi into square root of R prime into C prime and is the low cutoff frequency of the second order high pass filter. So students, let us now summarize what we have learned in this module. In this module, the various types of electrical filters were discussed. The difference between active and passive filters was studied, and the advantages of active filters were highlighted. The various types of active filters were studied in detail. The types of practical active filters were discussed. The expressions for gain in a first order low pass and second order low pass filter were obtained and the frequency response was discussed. The expressions for gain in a first order high pass and second order high pass filter were obtained and the frequency response was discussed. Thank you students for your attention.